All right, we're going to talk about center of mass today. It's one of the physical applications of some of the integration that we've been talking about. And for the center of mass, I think an easy thing is if you think about actually think about a sword, right? Going back um, uh, to fencing, say when we were fencing all the time, you think about a sword, and what we would do is we would take the sword and we would show where it balanced, and you wanted to have the balance, the weight closer to the um, the handle of the sword than towards the tip. So I'll try illustrating this concept here with this. A little hard to get it, but because it's just so. There we go. So if you find the point, what we would want is we would want that point where the blade, all right where it's balanced. Now, ideally, for something like a rapier, a sword, right, you'd want that weight towards the handle, but just depending on what the tool is for. In this case, this is just your basic, uh, basic hunting knife, right? And you see, or utility knife, you see where the point of balance is, right? Right there, a little bit in the handle, but about halfway. Now, what we're looking for when we do that is we're looking for what is called the center of mass. Okay. The center of mass is um, it's it's kind of so it's in physics terms, it's that point where if you apply a linear force, you push on it, if you will, at that point, you can move the object without causing the object to turn, all right, without causing the object to rotate. So that's that's what we mean by center of mass. The mass distribution, the way the mass, not weight, but the mass is spread out, is um, the same in all directions. All right. Now, when we are calculating that for more complicated shaped objects, so you see when we look at this thing, right? This is yeah, it's a knife. It's not a perfect line, but it really is kind of a linear shape, right? So you could treat it as a linear shape and it's relatively simple. But what happens when you get something more complicated, like this candle or this cup of coffee? All right. So that's kind of what we're going to talk about today. It's kind of building some more techniques to do that. So let's start simple. And what we're going to do is we're going to imagine a uh, a bar, right? A linear rectangular bar. And we're going to start with the simple formula here. The mass of an object is the density of the object times the volume of the object. Okay, so that's what we're going to start with, this basic thing. And now we're going to imagine this a linear or a thin bar or a thin wire. Okay. And what we're going to do is we're going to take this wire, and let's say we're going to impose a coordinate system on it, and the wire starts at x equals a, and the other, or the bar at the other end is at x equals b. And now what we're going to do is we're going to chop this thing into pieces. Okay, so this is the same technique that we apply with everything with integration, which says I'm going to take my interval, okay, in this case, my bar, and I'm going to chop it into pieces. And each of the pieces is going to have width delta x. Okay, so I chop my bar into k pieces, or n pieces, sorry, and each one has width delta x. Okay, that would be b minus a over n, say. And then we look at the kth piece of that bar. And the mass of that kth subinterval would be approximately equal to the density at a point from that subinterval. And so within each subinterval, we can pick a point xk star, and we'll measure the density at that point. And then the width of all those subintervals is delta x. And so the mass of the kth subinterval would be about the density at xk star times delta x, just like you see in this image here. Okay, pretty basic setup, similar to what we do with every integral. And now what we're going to do is we're going to take all of those subintervals, okay, and we're going to add them together. All right, so if the mass of my kth piece of my bar is about equal to the density evaluated at xk star times delta x, and then the mass would be approximately the sum of those n pieces. Okay, so that's the sum, k equals 1 to n of rho of xk star delta x. And then what we're going to do is we're going to take the limit as n goes to infinity, but we're doing it in such a way. What we really want to do, if you remember, is we want to do this in a way where delta x goes to 0, and then that makes n go to infinity, okay, of this sum. And in the limit, this becomes the integral from a to b of rho of x dx. And that is the mass of our object. Okay, so our one-dimensional object, our thin bar or wire, represented by the interval x equals a to x equals b, with a density function rho. And so the density doesn't need to be uniform, right? It can change along the wire, like, for example, this thing, right? The density of the handle here is different from the density of just the blade itself, right? So so the density can change along the length. The mass of that object is going to be the integral from a to b of the density function rho of x dx. Okay, all right. And so let's look at a simple example here. So in our example, we're going to imagine we have a thin bar, and the density of this bar varies along the length from x equals 0 to x equals pi, with the density function rho of x equals 1 plus sine of x. Okay. All right. Now, you can, we don't really need to graph the function here, because we're just applying the formula that the mass of this thing would be the integral from x equals 0 to x equals pi, in this case, of the density function, which is rho of x, 1 plus sine of x, times the density on each little piece, which is dx for us. And so all we're doing is we're integrating 1 plus sine of x from 0 to pi. And so that's x, the integral of 1 is just going to give us x. The integral of sine x should give us negative cosine x. And we should do this from x equals 0 to x equals pi. Okay, so we're going to have pi minus cosine of pi minus 0 minus cosine of 0, right? So let's see. Pi there, cosine of pi equals, trying to remember that. I think that's 0. All right, let's see. Cosine of pi is -1, so this is minus 1 minus 0 plus cosine of 0, right? Minus, so this becomes plus cosine of 0. All right, so cosine of 0 is 1, so we have pi plus 1 plus 1, so we get 2 plus pi as our mass. So all the center or all the mass problems like that are going to be basically the same, right? You have a mass function, you're going to have an interval, and you're going to have to integrate over that mass function over that interval. Okay, and that gives you the mass of the object. The next concept is the idea of work. Work is simply applying a force over a distance. Okay. So if I'm sitting here pushing on this desk, right, I'm applying a force to the desk, but I'm not moving desk, right? So I'm not doing any work. Okay. So work, physical work, is applying force over a distance. So the simple concept is force times distance. And so now what we need to do is we need to figure out, well, what happens if, it's simple enough if I'm applying a constant force to move an object over a distance. But what if that force isn't constant? I mean, think about it when you're actually pushing something heavy, right? The speed at which you're moving that thing isn't constant because the force you're applying isn't usually constant. Okay. So let's do a similar buildup like we did with the mass. So what we're going to do for the variable force thing is we're going to just assume we're moving an object over a linear distance from x equals a, x equals b, and we're applying a variable force to this that we'll call capital F of x. Okay, so this is just like a notional thing shown in this thing where the force is not, if it were constant, it would be a horizontal line, but it's not. It varies over the uh the distance that we're moving our object. Okay. Okay, so what we're going to do, like we usually do, is we're going to take our interval a to b here, and we're going to chop it up into n pieces. Okay. Each subinterval has width delta x, and we're going to look at each one. So we'll pick the kth subinterval, and we're going to say, okay, what's the work done by our force over this tiny subinterval? What does that look like? Okay, and that is just here. So on that kth subinterval, work is still force times distance. So we'll pick a point at x sub k star of our little subinterval here, and we'll say, well, what's the work done there? So we'll evaluate the force at xk star times delta x, and that's the little piece of work, approximately the little piece of work done on our kth subinterval. And then we'll add up our n pieces, and that is going to be approximately equal to the total work. Okay, I'm just going to write work so it's clear there. And then we will do the limit as delta x goes to 0, which drives n to infinity, of course. Of our sum. And then that gives us the integral from a to b, f of x dx, and that is our integral formula for work, like so. The work done by a variable force F, moving that object along a line, so linear distance from x equals A to x equals B, is W, work equals the integral from A to B of f of x dx. Okay, so now let's look at an example. One application or example that helps to visualize the whole work concept is the idea of a spring. Okay, and a spring is a basic physical object, right? We all know what springs are, but you can think the spring will be at equilibrium. So when the spring is relaxed, if you will, right, at equilibrium, no force is being applied to it. It's sitting at equilibrium, and that is our point x equals 0. Now, if we stretch the spring, we pull it from equilibrium, then the force applied to do that is greater than 0. And so we're moving it from x equals 0 to some x greater than 0. And then the other idea would be compressing the spring. So we're applying a force to squish the spring. Then the force is less than 0 in the distance because of the direction we're applying it, right? Force is a vector. It has a direction to it. And so in the compressed direction, F is less than 0. And so we're moving it from x equals 0 to a point x less than 0. Okay, so that's our basic spring setup. According to springs, follow something called Hooke's law. According to Hooke's law, the force required to keep the spring compressed is or stretch. So if we're gonna compress it and then hold it, or we're gonna stretch it and then hold it, the force required to do that, to keep the spring in a compressed or stretched position x units from equilibrium, is f of x equals k times x. K is a constant that's dependent on the spring. Okay, so as that constant it's related to something called Hooke's modulus. We won't get into that and take your first physics class. You'll talk about that. But it's a constant related to the spring. Okay, so to stretch the spring to a position x greater than 0, you need a force F greater than 0 in the positive direction. To compress the spring, you need a force F less than 0 in the negative direction. But either way, the force required to keep the spring there is F of x, it's K, which is the spring constant, times x, which is the distance that we're displacing. Okay, so that's our variable force. And so let's look at an example working with a spring. So we'll start with, this isn't particular to this problem, but this is the basic idea of Hooke's law, right? That the force required to compress or stretch your thing, to move it from equilibrium and hold it in that place, is k times x. So it's linear, right? And so what we want to do now is we want to say, okay, let's suppose, let me switch screens here. All right, so we'll look at an example here and we'll say, all right, let's suppose I have a particular spring and I am going to, looking around, I don't really have a spring handy. But so the force required to stretch the spring 0.1 meters from equilibrium is 10 newtons. Okay. And then we want to know, well, what's the work done to compress a spring, the same spring 0.5 meters, or to stretch it 0.25 meters? The first thing we need to do to answer other questions is we need to know what K is. So assuming this spring obeys Hooke's modulus, we would want to figure out what K is. And so step one is, so we're doing A here. Step one is we know that 10 newtons, right? That's the force to get to X equals 0.1 meters. And so the force at 0.1 meters, it says, is going to be K times 0.1 meters, and that is 10 newtons, it says. And so K is going to be the 10 divided by 0.1 meters. And if you're interested in the units, which you should be, right? Newtons is kilogram, meters per second squared, right? From Newton's second law. Okay. So this is 10 kilogram meters per second squared divided by 0.1 meters. And then there's the second squared down there, if you care about that. Well, right, the meters are going to cancel. And so 10 divided by um, oh, sorry, 10 divided by 0.1 is going to give you a K of 100. And actually, we'll go ahead and we'll clean this up. So just because the example we're doing is a little cleaner, so it's Newton per meters. And so we're not going to reduce the units here. So we'll just do Newton's meters. So K is 100 Newton meters. And so now anything else I want to do, I can use this value of K. So up here, so it's all right. K is 100. We just solved this Newton meters. All right, now let's answer the next question. Okay. For this same spring. So remember, K is tied to the spring. For this same spring, I want to compress the same spring 0.5 meters. Now, if you're compressing the spring, right, the way we set up our coordinate system, I'm going to go back to here just to show we're talking about the way we set up our coordinate system at equilibrium, X is 0. If I'm going to compress it, so we said, hey, if I'm going to stretch it to 0.1 meters, it's going to take me 10 newtons to do that. So the spring constant in this case is 100. Well, now for the next thing, I want to compress the spring. And so that means I'm applying a negative force to achieve a negative displacement, X less than 0. And so jumping back over to the board here. Okay, now I want to compress it 0.5 meters, which means I want to go from 0 to negative 0.5. And it's f of x dx. Well, for me, right, f obeys Hooke's law. So Hooke's law is k times x. So it's going to be the integral from 0 to negative 0.5 k times x dx, and k we just found is 100, so it's the integral from 0 to negative 0.5 of 100 x, and so this gives us 100 x squared over 2 evaluated between 0 and negative 0.5, and that works out to be so 50x squared, that works out to be 12.5. Okay, and it's Newton meters because it's work, so that's the work. Okay, next one, C, same idea, but now we're stretching. So now we're going from 0 to 0.25, not 2.5, sorry, 0.25. It's still 100x dx. And so we know, right, so it's going to be 50x squared evaluated between 0 and 0.25. And that is going to work out to be, in this case, 3.125. Okay, Newton meters, which, by the way, another way to write Newton time meter is something called a joule. That's the unit for force. Okay, so that's our spring example of a variable force applied over a distance for work. All right, so now let's go back to there are other applications of work and variable force and things like lifting, pumping problems, stuff like that. But we want to get back to the center of mass. Okay, so so the work is just another example of it's the same type of concept. Take your interval, chop it up into pieces, figure out what's happening on the little piece. Okay. And so to calculate the mass, we just saw we chop up our linear thing into pieces and we calculate the mass in each little piece and add those up. And then the limit that turns to an integral, and we have the mass. Okay. We did the same thing for work. But now we want to get back to the center of mass idea. We talked about what the physical concept is, right? It's balancing. And so let us look here, going back to our linear ideas. We have this linear thing. Think about a seesaw, right? Put a mass on one side, a mass on the other, and you have the pivot point, right? The center point, and the seesaw balances. It's a simple lever. So provided that the mass 1 times the distance from the center point and mass 2 times the distance, its distance from the center point, provided those two things are equal, then this seesaw balances. So what we're saying is in our linear setup, if m1d1 equals m2d2, then that balances. Okay, great. Now what happens though if I have several objects? Okay, what happens if I have several objects? What do I do there? But before we do that, before we get to the multiple objects, in order to get there, right, we need to generalize this concept. And let me draw up 4. All right, so we had our center point, our balance point, right? And we had our mass 1, d1, then we had our mass 2 at a distance d2. That's our basic setup. Okay. What we're going to do in order to generalize this, like we're normally going to do, we're going to impose a coordinate system on this thing. And we're going to say that the balance point here, balance point, has a coordinate x bar. And so the distance d1, so if we've stuck this coordinate system on there, okay, say this is x equals 0, and then this is x coordinate x2, this is coordinate x1, right? So arbitrary coordinate system, okay? 0 doesn't necessarily has to be there. We're just saying we're sticking a coordinate system on it. And the coordinate of mass 1 is going to be x1. And what we care about is the distance from mass 1 to the balance point, which is at x bar. And so that distance is going to be given by x1 minus x bar. And that has to equal mass 2 times whatever its x coordinate is, its distance from that x coordinate to x bar. X bar is our center point, right? Whatever that center point is. Okay, great. Now, let's suppose that I want to know, okay, if I know mass 1, I know its coordinate, I know mass 2, I know its coordinate, then what is the center point, right? So we would take this and we want to solve for x bar. Okay, we could do a little bit of arranging. I'll save the algebra for you, but suffice to say that the solution after some, so clear your parentheses, well, solve for x bar, you're going to get m1 x1 plus m2 x2 divided by m1 plus m2. That is going to be your center point. And that is the center of mass for this problem. Okay, well, now that we've done that, okay, now that we've kind of generalized this, so we can do it arbitrarily for any coordinate system here. Now we want to consider first an example problem. Okay, so for our example problem, blow this up here. Okay, here's our example problem. All right, so here's our how we found the center of mass. Now let's do an example problem. So let's suppose that we have a balance point. So we've put a 160 kilogram gorilla on a seesaw. We have an 80 kilogram man on the seesaw. This thing is balanced. And so at that point where it's balanced, the we want to figure out, okay, what's the center of mass of the system? Okay. And so we see from our coordinate system that the 80 kilogram man is 2 units. Okay, from the 0 point. We found the balance point. Where is the balance point? Okay. So from the way we defined our coordinate system, our 80 kilogram man at 2 plus 160 kilogram gorilla at -4 plus the sum of their masses, 80 plus 160. And we're going to get that -2 is the center of mass. So that's going to be the point where this thing is centered. Okay. All right. Now we can generalize this to multiple objects. Before I do that, I should share the screen I just wrote all this on. So this is just a simple, right, for our problem setup that we had there, right, just simply plugging in the formula to get x bar equals -2. So that's our center of mass there. Now, suppose we have multiple coordinates, okay, multiple objects. We're going to put, instead of just 2 things on a seesaw, we're going to put a whole bunch of things on a seesaw, and we want to figure out where then is that thing going to balance. Well, the idea is going to be the same. Okay, we're just going to generalize it, but it's the same as the two object setup, really. So for two objects, what we were basically saying is these two things had to be equal. And since we're defining the coordinate system, so some of the things, right, some of the masses are on one side of the zero, some of the masses are on the other side of the zero. And so this works out to be that the sum of these two things had to be zero. Okay, they had to be equal, but on opposite sides of x equals zero. And so we get this. All right, so now let's generalize this. Suppose now I have a seesaw and there's x equals zero somewhere in there, and I got some masses. Right, so maybe I've got M1, M2, and I got M, however many. MK plus one, you get the idea. So I've got a whole bunch of masses, some on one side of zero, some on the other side of zero, but they're all balanced out. Okay, the seesaw is perfect. Okay, so if that's the case, it's the same idea. M1 times X1 minus this X bar, okay, plus M2 times X1 minus X2 minus X bar, plus dot, dot, dot. If I have N masses, there's sum of these quantities must be zero. And so the balance condition, the equilibrium condition, works out to be the sum from k equals 1 to n of m k xk minus x bar has to equal zero. Okay, so now this is a system of n equations and n unknowns, and we'll save the algebra, jump right to the solution here. Okay, and you'll notice it's analogous to the two object thing. And that is your center of mass for n objects. Okay. Now we can take this setup and we can move it to our linear bar, right? Our wire or thin bar idea of variable density where the mass varies along the bar, and we can turn that into a center of mass problem. Now we can figure out, okay, so here's my object of varying density, right? Density is different here than it is here. And we can figure out where, if I put a coordinate system on there, where would the balance point be? Okay. And using that same condition, the same idea that the sum has to be zero, where would that point be? And we're going to do the same idea. We're going to chop our bar. Remember, the density rho of x, the density varies as we move along the bar. So density, mass per unit length varies with x. So that's a function rho of x. Okay, we have a bar running from x equals a to x equals b. So it's got a coordinate system applied to it. And we're going to do the same idea. We're going to chop that bar up into n pieces, okay, and subintervals. And we already saw from before that the mass of the bar on the kth subinterval was going to be the density at some point on that interval. So rho of xk times delta x. Okay, that's what we had before. And we know that the total mass, we add them all up, gives us this integral here on the left. But let me jump to let's build it up a little more slowly here. So remember, we said that x bar is the sum of the mass times xk over the sum of the mass, right? Well, that's all we're doing here, except remember, for the variable density bar, the mass mk is the density at xk times delta x. Okay, so we're summing k equals 1 to n of the m sub k, but that is rho of xk times rho at xk times delta x, and then times x sub k. And then the bottom is the sum of the masses, but each of the masses m sub k is rho of xk delta x. And we take the limit as x goes to 0. And in the limit, we get this. Okay, so it's the total moment is what the top is called over the mass m. Okay, so you get the integral rho. Well, let me write this down. You should be able to see it, but integral from a to b of x rho of x dx divided by the integral from a to b of just rho of x dx. That is the center of mass x bar. And so you can see the formula put together here. Okay. This is your center of mass. So we'll finish up center of mass with an example. Okay, so we'll look at an example where let's suppose we have a 2-meter metal bar. Okay, and this metal bar is made of an alloy with the density varies with 1 plus x squared, where x runs from 0 to 2, so along the length. And we want to calculate the center of mass. All right. Find the center of mass. All right, so first we need to know the total mass. Total mass is the integral along the length from 0 to 2 of 0 to 2 meters of rho of x dx. So that's just 1 plus x squared dx. Okay, and that's going to be x plus x cubed over 3. This thing evaluated from 0 to 2. And so that's going to work out to be 14/3. Okay. The second one is the total moment. Okay. And that's the integral from 0 to 2 of x rho of x dx, right? That's what it should be. And so that's going to be 0 to 2 of x 1 plus x squared dx. X plus x cubed. X squared over 2 plus x the fourth over 4, evaluated from 0 to 2, and that works out to be 6. And so x bar is going to be the total moment divided by the total mass. And so that's going to be 6 divided by 14/3. And so this is 1.29 meters. So at 1.29 meters along the bar is where the balance center point would be. Okay. All right. So that is center of mass. I used kind of we had to use some slides for different things because your last textbook did center of mass, waited till chapter 16, but it's not that it's complicated, right? You're doing a one-dimensional thing once you jump to two dimensions. So we looked at, let me give you a simple example here, since I'm doing that, right? Well, okay, so I don't have anything hand, but let's just do a simple example of something like this. Right now we're talking about a an irregular density object that's two-dimensional, right? Even though I can treat this as a thin plate. Okay, because it's a two-dimensional object, you're going to need Calc 3 to do that. So you're just going to have to worry about objects that are basically one dimension. Okay, bars, wires, things like that. The density varies along the length, and what's the center of mass of that thing. Okay. All right. So that's it for center of mass. So mass of objects with regular density, center of mass, and work, variable force applied along a linear distance. All good Calc 1 or Calc 2 applications. So let me know if you have any questions.